Okay, now we're going to look at some circuit problems that have resistors in parallel with each other. So when things are in parallel, it means that you have a battery, a voltage source, then you've got a circuit, and you've got a wire that at some point splits into two parallel circuits. So at this point, you have two different paths down which the electrons can flow. And they're parallel to one another, and that's where the term comes from. And then at some point, those two paths come back together. So you have these two different paths, and they're gonna rejoin here. So you've got points at which the two paths have joined, and you've got points at which those paths split apart from one another. Okay. The thing to remember about parallel is that any given electron only goes down one path. So if you're an electron and you're exiting the battery, moving down the wire, you're either going to go down path 1 or path 2. You can't go down both paths. And so if you think through for an individual electron, how much does it have to travel through? Well, an individual electron only goes through one light bulb or the other. And when electrons go through light bulbs, they spend their voltage there. If they have to go through 2 or 3 light bulbs, they have to split up their voltage like they did in the series questions. But in these examples, where I just have one light bulb on each path, it means that any given electron will spend all of its voltage at the light bulb that it goes through. So what do I mean? I mean that if the battery gives 100 volts, there's going to be 100 volts given to this light bulb, because if you're an electron that travels down this path, you will spend all of your voltage at that light bulb. And if you're an electron that goes down this other path, so in blue, then you're going to spend all 100 of your volts at this light bulb. So the voltage given by the battery is not split across the two paths. It's actually the full voltage is given to each path. At least in this kind of setup where it's actually quite simple and there's really just two light bulbs. There are more complex setups where that statement isn't true, but for now, that's fine. This statement holds true. Okay, so we know the voltage, and if you look at each path, we know the resistor value at each path. So we know that the first path has resistor of 10 ohms, and the second path has a resistor of 20 ohms. So we can use Ohm's law now that we know the voltage and the resistance for each light bulb, and we can find what the current must be. So voltage over resistance, resistance 1, and then we're going to have voltage over resistance 2 to find out the current in the second path. Well, if we have 100 volts and the resistor is 10 ohms, that gives us 10 amps down the first path. So I should do that one in red to make it more clear that we're talking about the red path. So you can see each path sort of has to follow Ohm's law on its own. If I look at the next one, I've got 100 volts, but I've got twice as much resistance. And so that means I get half as much current flowing. So down path 1, we get 10 amps, and down path 2, we get 5 amps. The total current is 10 amps plus 5 amps, so 15 amps. So it's a bit flipped from series. In series, the current was the same everywhere, and the voltage was split. In parallel, the voltage is the same across each path, and the current splits. So at this point in the circuit, you would have 15 amps coming out of the battery. Then it splits, and you get 10 amps going down this path, and you get 5 amps going down this other path. And then they come back together, and here you'd have 15 amps again. So the current is said to split when it reaches a junction. A junction is where the path splits. So the current splits, and then it comes back together. And so if you have 15 amps going in, you also need 15 amps coming out. And the current on the paths should add up to that. Okay, now we can use our total current and our voltage, which we already knew, 100, to solve for the equivalent or the total resistance. Voltage over current equals resistance if we use the total current value. So we know the total voltage is 100 volts, and the total current is 15 amps. And so the total resistance, if we divide this, is 6.67, 6 and 2/3. And that will be the ohms that this is acting like. Now, I find this is very counterintuitive, that you can combine a 10 ohm resistor and a 20 ohm resistor, and somehow the total resistance is actually less than either one of the individual resistors, let alone their combination. That is quite counterintuitive. Now, why is that? It has to do with the fact that because we gave more paths, we've actually made it easier for more current to flow. And the analogy I often use is if you're at a store and they opened up a second register, a second cash register, that would allow more people to flow through the store because now there are more pathways. And so even though you're technically adding in more resistors, you're also adding in more paths. And so the more pathways you add, the lower the total resistance is to that current in this circuit. So more pathways equals less resistance. So because of how they're arranged, we actually lowered the overall resistance, and that's why we got such a huge amount of current flowing. Okay, we can try one more time. This time I'm using the resistor symbol, a scribble version of the resistor symbol instead of the light bulb symbol. Okay, so again, the first thing to start off on and remember is that the total voltage is going to be lost across each path. So this path gets 20 volts, and this path gets 20 volts, and this path gets 20 volts. So they all get 20 volts because any given electron is only going down one path. So they deliver all of their voltage there. Once I know that, I can solve for individual current values with Ohm's law. 20 volts divided by the 2 ohms of resistance. So down this first path, I'm going to get 10 amps. Down pathway number 2, I have a voltage of 20 again, but I have more resistance. I have twice as much resistance, so I should get half as much current down pathway 2. And down pathway 3, I also have 4 ohms, and so I should also get 5 amps down pathway 3. So I've got 10 amps down this path, I've got 5 amps down this path, and I've got 5 amps down this path. So in total, I4, what do I have out here? Well, I4 is one of the places where all the paths have come back together. And so I4 should equal 20 amps. So the paths are all together here. Then this is the junction where they split. There's actually sort of multiple junctions, but there's 20 amps that go into those junctions. And so when they come back out, it has to be 20 amps again. That's the combined current. Okay. So now we should be able to figure out the equivalent resistance using this total current value and our total voltage value. So voltage over current tells us what the resistance must be. The total current, we said, is 20 amps, and the total voltage was 20 volts, and that means that the total resistance is actually 1 ohm. Okay, so you combine a 2 ohm resistor, a 4 ohm resistor, and a 4 ohm resistor, and they actually add up to, they are equivalent to 1 resistor of 1 ohm. And that's why we use the term equivalent resistance. Now, this last equation is quite tricky. It's a look ahead at what we're going to strive for. This would be a way we could have solved for this 1 ohm value before doing any of these other steps. So if you have 3 resistors, and you got a 2 ohm and a 4 ohm, and a 4 ohm, and they are arranged in parallel. So there's a path, 3 different paths. Okay, the equation is that the equivalent resistance is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance, and so on, with as many different pathways as we have. So let's see how that works out with these numbers. So I'm going to do 1 over 2 ohms. I'm going to do 1 over 4 ohms. I'm going to do 1 over 4 ohms. Now, we've got to work with fractions here and have common denominators, essentially. So 1/2 is the same as 2/4. And so when I add all these together, I would have 4/4 is the same as 1 over the equivalent resistance. And then I need to flip it. So this is 2 over 4 ohms. And when I flip it to get the equivalent resistance on the top. In this example, it actually stays as the same value. It stays as 1 ohm. We can look at the previous example also to see how that equation works. If I had a resistor that was, I had one that was 10 and I had one that was 20, so I'm going to try that down here. So I have to do 1 over 10 plus 1 over 20. So common denominator, 1/10 is 2 over 20 plus 1 over 20, which is equal to 3 over 20. Okay, now that's 1 over the equivalent resistance. So the last and the trickiest step is that you've got to flip these two to actually solve for the equivalent resistance. So 20 over 3 instead of 3 over 20. 20 divided by 3 is 6.67 ohms, which is what we figured out with all these other steps in the first question about parallel, right? There is another way you can get there, but this equation allows you to immediately figure out what the equivalent resistance is using this equation. So that's pretty tricky, but it's something that we're going to try to practice more of in class.